Hello everyone, so today in this tutorial I'll be walking you through the assignment 2 of Comp 310 in order to give you a quick start so that you can get going as soon as possible. As you can see, this assignment will take longer than the first one and you only have 2 weeks to complete it, so better start now. So what I'll be covering will be part 1.1 and part 1.2 of this assignment. So setting up the empty backing store for paging and the partitioning of the shell memory, okay? So looking at the code here, I believe you have a Docker file if you're not running on Linux. I'll be just running it directly in the terminal, but it doesn't change anything on your end. So just to build the shell, just type make here. Mine is already built, so I can just call it my shell here. And as you can see, it's pretty much the same thing that you had with assignment 1. The only difference is that we're actually going to build the paging infrastructure, right? Okay, so we can just quit. And so the first thing that is asked of us is to set up the backing store for paging, right? And the backing store is the part that the hard drive is used by a paging system to store the information, not currently in the main memory. So in this assignment, we'll be representing it as a directory, but in real life, it's a bit more complicated. So we want an empty backing store directory that created when the shell is initialized, and it should be created inside the current directory, okay? So this part is easy. And in case the backing store directory is already present, we'll just remove it, okay? And finally, when we quit the terminal and with the command quit, we'll be deleting this backing store directory, right? So this is the very first thing that we're going to do. So the main function of your program is in the file shell.c over here, I believe. Yeah. So this is the entry point of your shell. So this is where we'll be implementing our backing store directory, right? So I guess we could do, we'll add a to-do over here, create backing store. Directory, right? And if it exists, we'll remove it, okay? We'll remove it. And finally, when we exit the app, we're gonna remove that thing, okay? So the main function runs after initializing the memory, runs into an infinite loop until something else breaks. So we'll cover the quit command later on today. So how should we go about creating the backing store directory? So since it's just a folder, we can just use the command make directory, right? So as soon as the program begins, we'll create a directory. And one way to do this is just using the system wrapper. And in quotation, we can make any system call. So I'll just call makedir, right? Makedir, and it's in the current working directory, right? Yes, it is. Yes. So makedir, and we'll call it backing store. So just literally creating a folder here, and that's really all we need to do. Okay. So we'll compile it. Just give me a second. Make. Okay. So let's look on the left over here, and normally when I type my shell and I press enter, it should create the backing store. Yeah, so as you can see, a folder was created, right? So we got that part covered. But now, what if I do it again? Okay, as you can see, we have a message that is printed here. It says cannot create directory because backend store exists. So if it exists, we want to remove it. And a lazy way to do it is actually to remove it, whether or not it exists. So I can just write another system function, and inside of it, I'll just type rm backing store. And since this is a directory, we're gonna put the -r here, and we'll force it even. All right. Okay. Let me quit that terminal. Remake the app. Oh, I forgot the semicolon. All right. Okay, so we had no error message here, but now what it's doing is just removing the folder and creating a new one. And to make sure this is really what it's doing, if I create this file ttt, you know, and when I exit and relaunch the program, as you can see, backing store was indeed deleted since ttt was deleted as well. All right. So in order to delete it before the application, when we type quit, we'll have to walk through the actual function quit. So once your main function is running, it's calling the parse input over there, and it's gonna redirect us to eventually the parse input function, the interpreter. Okay, so the core of your application and your commands will be an interpreter, and quit is going to be probably around here. Let me find it. Yeah, return quit. Okay, so this is the function quit. So right now it's just printing by and destroying the ready queue over here. So I guess after destroying it, destroying the queue, we can just make a system call once again, removing the rm backing store. Okay, make sure you spell it right. You can call it with any name you'd like. I call it this way because I'm used to it, but you know, feel free to be creative. Okay, and then when I call my shell, so the backing store exists, but when I quit, it is being deleted. So part one wasn't complicated, and but of course, it's, you know, you're going to need to do much more than just setting up the empty backstore for paging, right? Eventually, when we call the function, for example, within the shell, we will want to do exec prog1, prog2, prog3, like this. And for each program here, those are files on your computer. They will need to be copied over to the backing store for each and every file. And from the backing store, they will be paged into our virtual memory, so to speak. All right. Speaking of virtual memory, let's jump right into part two. This one is a bit, will take a bit longer. So the shell memory will be split in two parts. The frame store, so this is a part that's reserved to load the pages into the shell memory. And one thing to keep in mind is that the total lines in the frame store will be a multiple of the size of a single frame. Yes. Okay. So what does this mean exactly? So each page of the assignment is a frame, and this frame will have 3 lines, and I mean 3 lines of code. So literally, so let's look at a program here, okay? So in order to be executed, this program will be copied over to the backing store and to the frame store. The frame store will be used by the page table, and each page will point to the frame store, but we'll see that in a bit. So bear with me for a second. So we said the length of a frame will be 3. I don't know if someone told you, but yeah, it's 3 lines of code. So echo here, set here, and that echo here, they all belong to page 1. Okay? And the next line doesn't fit on the first frame or the first page. So it's going to fit into page 2. Okay? So in order to have this program into memory, you will need 2 pages, right? And same for this program as well. So you have the first 3 lines will be page 1, the rest will be page 2, okay? So this is basically what the frame store is for, okay? So 3 lines, and we want the frame store to be a multiple of 3, so that, you know, a whole number of pages can fit into it, okay? And so this is one part of the shell memory, and another part is a variable store. So whenever we store a variable and we assign it a value, this is where we'll be storing those values in the variable store, okay? So those 2 components will be the shell memory, okay? So let's look at the shell memory file. As you can see, you already have a memory struct here. So it's nothing complicated. You have basically a key value pair here, okay? And the name of your variable would be here, and its value would be here, okay? And here you basically just have an array of this key value pair. So see that as a map or a dictionary in Python, okay? It's nothing more complicated than that. And the memory length here is 1000. So you have effectively 1000 key value pairs into your shell memory. So that would be the hard limit, okay? And so inside that that memory structure will be the frame store and the variable store, okay? And that's pretty much all we have over here. You have a bunch of functions here. For example, you have the shell memory over here to print it. You can print the shell memory just for debugging purposes. But the rest is pretty much up to you. You also have helper function, of course, to get some memory or set some memory to this the struct over here. I think get value at line, so you would give the index and you would get the value, or you could free the memory and so on. Okay, so I'll give you a more concrete example of what I'm saying. Perhaps that'll be more helpful. Let me just share my screen. All right, so I'll draw you a representation of the shell memory, okay? So this is your shell memory over here. Memory, and this is just a list, right? All of this, you know, that will be a long list, okay? I'll write the indexes, but those are not key value pairs, they're just indexes, so that you can, you know. Okay, and each of them contains the memory struct, which I'll represent it in a JSON way, but it's basically var and value, right? So you have a a string for the var name, and you also have the value, right? And these are strings, okay? So imagine you have that for multiple rows. So I'll duplicate that over here, over there. So how are you supposed to create your shell memory with this system, right? We talked about frame stores, we talked about variable stores, but how do you do that concretely? So you already have everything you need with just this data structure, but it's up to you now to configure it, right? So there are two ways to approach this. One way would be to create a data structure just for the frame store, right? So you would have a struct that contains key value here, okay? And the frame store is nothing more than here, for example, if we go back to a program1.pdf, okay, I'll remove these. So the frame store would store the content 3 lines at a time of a program. So echo hello p1, I'll just write this one out over here. So you would have right here echo hello p1, right? Then what's the next line? Set x to 10. Okay, let's do that. Set x 10, and finally echo x, right? We're gonna echo x like this, right? So this is okay. So this is now the what's it called? Was it called the frame buffer? The frame store, right? Okay, so this is now our frame store, but it's also the same data structure of the shell memory, right? It's just an array. So our frame store, we could just arbitrarily say that, you know what, it's the frame store will be the 6 first indexes of the shell memory here, okay? And I'll draw a hard line. I'll make it red to be, super hard. And then anything after that will be the variable store. So that's one way to do it, okay? So if I have 6, actually here we have 7 since it starts at 0. So let's pretend 6 never happened, okay? So it stops at 5, and as you can see, so in our frame store, we can store up to 2 pages. So you have 1 page here, 1 page here, okay? And after that, if we cannot, we're gonna evict the pages that are here if we need to load any more pages, okay? But essentially that's it, okay? And where does the page table come in? Well, it's gonna come in, well, for every process that is being created, for example, and your page table structure, let's define a page struct, for example. It's gonna have a page index, okay? And this is just a variable that contains, this is just an int array, okay, of length 3, for example, okay? And what it's gonna contain is just the indexes of the page. So let's say we have page 1 over here, okay? And page struct, just so that we're clear. Okay, so this is our page struct. So the page index, we'll just refer it as the indexes in the shell memory where our page will be, okay? So this is an abstraction of the actual frame store. You know, at the program level, we don't actually care where exactly in the frame store is our data, but we just need pointers to it, right? So we'll be on indexes 0, 1, 2, okay? So that could be a way to do it. And then you have, so that would be an element of the page struct. I'll just rename that to, for example, index, right? I mean, I could have called it page index, but in my notes it's index, right? So it's just an int array of 3. And we also have another array of ints, for example, valid bits, okay? And that will come into play to define, you know, what bits of the page are actually being used, for example. One good example of this is this program. Okay, so the first 3 lines are allocated for, you know, to page 1, and this is page 2, but, you know, page 2 could take 2 more lines, right? But the code stops at, you know, the very first line here. So one way to approach this would be to go back to our page struct over here and say the first one is valid, but not the other 2, right? Because over here there are no data related to our program. So, and then a useful thing to have would be the PID of your application. You know, every page is tied to a PID, so you could have the PID, which would be an int, and I guess the page index. You know, which should be an int. Is it page 1? Is it page 2? Is it page 3? And so on and so forth. Okay, so that's one way to do it, to have the shell memory over here, and have it set at a border between the frame store and the variable store. Okay, so I hope that cleared things up. I'm just gonna write it hard-coded into the code, so it'll be more helpful, I believe. So you have your memory struct over here, but I guess a good way to put it would be near the PCB, okay? So this is in this struct that a program counter is being stored, and everything related to your program. Actually, we should walk through the code from the very main function and jump into every part of a process call. So let's go there. We said that it starts as shell.c, right? Shell.c, and then interpreter. And then you have the exec call, right? And inside those calls, you have the command arguments. And as you can see here, what we're trying to determine is how many programs are we running, right? Because we can run program 1, program 2, and program 3. Like we can do this that way. So prog 1, prog 2, and prog 3. And I think you need the scheduling algorithm, right? So we're just going to use round robin. So basically everyone, you need to take their turn. So we'll start with 1. We'll execute it for a certain amount of time. And by amount of time, we mean lines of code, really. So let's say that the slice is 2 lines of code, okay? So program 1 gets executed for 2 lines of code, then program 2, then program 3, right? Okay, so this would be a valid command as well, just prog1 and prog2, and so would this. Okay, so what this code does is just figuring out how many arguments are being passed, and if it's just one with just prog1, the last two are null. If it's two arguments, you get the idea, right? And eventually we're going to call the exec command over here. So file name 1, file name 2, file name 3. Okay, so remember when I said that the backing store would eventually need the program files that are being called by exec. At this time, you now have the file names here, so it would be a good idea, I could have a to-do line. We're not going to cover it in this tutorial, but it could be a good idea to, hold on, this is a bit weird. Okay, VS Code is having a hard time. Okay, so like I said, you have the frame number over here, the file number, I mean, and a good idea would be here to copy the files. Okay, so I'll add a to-do, copy files to what's it called? Backing store. Okay, or you could do it somewhere else, but I thought of doing it here. Next, process initialize fname. Okay, this is all good. What else? Yeah, so everything seems to be inside process initialized. So let's click into that function and see what's going on over there. Okay, so inside that function, you have the file pointer. Okay, so it's going to take the start and the end of that file, and it's going to make the PCB. Okay, so this is what creates our process. Okay, so we make a new PCB, start and end. And these are pointers to ends, right? And they represent the start and end of the lines that we're going to run, I believe. Okay, and inside the PCB you have all the parameters of your PCB. Okay, but you might need to add some more, right? For example, you might need to add a page table. To do add page table. And what is a page table? So it's an array. It's an array of pages, for example. And if you have an array of pages in the form of double pointers, you might also need the number of pages. Pages. I guess you could have int number pages like this, right? Okay, it's a bit verbose to call it number of pages, but you get the idea. In here, it could be a double pointer of a page object, okay? Page table, for example, right? So that would be a way to do it. But for that to happen, we're going to need our struct, our page struct, right? So why don't we go into here and define, type def struct page. Okay. So what is a page exactly? So like we said earlier, a page can contain the index, right? So index 3, right? Because it only has 3 lines of code. But if you are to do this, you should have a variable that points to it, because we don't like numbers just hanging around like this. You have valid bits over here. You have the page index. And finally, you have the page bit, right? Okay. Actually, don't need the type def. Just a struct will be enough. Okay. So here I have defined my struct page. Actually, I'll do the type def on top, so it's clearer. Type def here. Struct page. Awesome. Okay. So it should be blue eventually. So we have basically our page structure. And at some point inside the code, when you put, you would have to create a function that pushes the data to the frame section. So let's go back to shell memory. Right over here, you have the memory. So shell memory here, is where our, where the frame store and the variable store are. Okay. And eventually we need a hard line, a cut or a threshold. So you could have just variables like, for example, frame size. So frame size equals, actually it's a frame store size, right? I only want to store at most 2 pages. Okay, this is a bit, cheap, but, and then frame size. This is actually 3 lines of code, right? This is the same as a page. So 3 times 2 is actually the memory section. Okay, so you could say the hard line or the threshold. So from 0 to the threshold, this is the frame store, and everything after that until like the 1000 line over here, everything after that is a variable store. Okay, equals a frame store size times the frame size, right? And make that a const. That'll help. Frame store size. What's wrong with that? Must have int expression, must have a constant value. Okay. Const. I'll just make that a const as well. Okay, so we have our threshold over here, and this is also a const. Okay, but define it however you like over here, and you could have a helper function, so to speak, that will allow you to create a frame. But that goes a bit beyond the scope of this tutorial, but function to alloc a new frame, right? And let me check what we have in store. Don't forget to initialize the content of this shell memory, because since this is C, we'll have 1,000, an array of 1,000 indexes, but all the data will be garbage, so make sure you have initialized your data. Well, meminit is a great function. Right here, it does exactly that, in fact. So what it does, it takes the shell memory at index I here and the variable, it set it to none, and so the same goes for the value. These are strings, recall. So that's how they do it. So okay, you can set the value here. So in your framealloc function, that would go here. You would call these functions, for example, memSetValue, to allocate a frame. All right. And that's mostly, yeah, that's pretty much the entire tutorial. Let me see if we checked it. So variable store to accomplish this, when data structure. But again, the way I did it, you can do the same thing in a completely different way. It's really up to you. So long as all the data ends up in the shell memory at the end of the day, it's perfectly fine to do it your own way. So hopefully that cleared things up, and if you still have questions, don't hesitate to ask on Ed. All right, see you later.